Hello. Today we're going to be talking about Today we're going to be talking about chapter 6. This was pre-recorded before we covered material on Wednesday, so if we did not get finished on Wednesday, we will come back to chapter 9 on the following Monday. But I'm assuming that we're on schedule, and we are starting chapter 6 on Friday, and we'll be in chapter 6 and 18 for the rest of the semester. These are the last two chapters. This is the last real chapter we're going to be covering. Chapter 18, we're only doing a couple sections of it. So, yay! And chapter 6 really goes into depth about the thermochemistry of reactions and how they're occurring, and digging deeper into how reactions, like the details of these reactions. Now, we talked about energy in chapter 7 and in chapter 8, and there's different definitions that you have to consider. Now, when we're talking about bonds, these energies that we're talking about is the potential energy. So while we do not have clickers going on right now, please note that there will be a quiz opening up based on these video lectures to make sure that you are listening and paying attention. The quiz will be shorter than normal, and will just be a couple questions that refer to the content that was covered on these slides and also the audio. So just because it's not on the slide does not mean it's not on the test. So please make sure that you're paying attention and taking notes as we go through. So different definitions of energy. There's kinetic energy, there's the energy of light, there's the energy of bonds, and polarity is not actually a type of energy, it is just a description of a bond and how electrons are being shared. Kinetic energy is, if you think about kinetics or Kinect, the Xbox Kinect, it moves, you're moving, and it's detecting that. It cares about how fast you're moving and things like that. Potential energy is how much energy you have stored. And all this goes into depth in chapter 6 and chapter 18 when we talk mostly about potential energy and thermodynamics. Specifically, we're going to be covering thermochemistry, which is just the study of the energies of reactions. So this could be energy absorbed or used, or energies that are given off as products. Thermodynamics is the study of heat transfer or heat flow. So heat is a type of energy that we'll learn about in a moment. But what is energy? There's two different ways of describing energy, at least. Energy is the ability to do work or to transfer heat. What this means in terms of what we're going to be doing is energy is described as the kinetic energy and the potential energy. Okay, so we care about how things move and how they work, and we care about the energy stored in a system. Now, it gets really complicated later on when we talk about energy and thermodynamics and thermochemistry in various different terms. So there's enthalpy, which is the transfer of heat and learning about heat. There's entropy, which is the study of chaos, which is in chapter 18. So it's very important that you work through and maybe read up on these types of energies to make sure what we're using and when to use it. Potential energy. So before we go into the chemistry definition, let's just think real world application. You have a car, okay? How did that car get up on the hill? You had to put energy into it to make it move, right? While it's on that hill and it's not moving, you can see it's kind of stuck, isn't it? Gravity is acting on the car. So there is a force acting on it. Okay, it has a potential energy. It has some energy stored into that system. Once it starts moving, it's losing that potential and being converted to kinetic energy. So the potential energy, represented by PE, decreases, but kinetic energy increases. When we think about in the chemical sense, we can relate potential energy and kinetic energy to chemical and thermo energy. Chemical energy, breaking bonds, forming bonds, is how we describe, or it's described by the potential energy. So it's the energy of a substance due to the potential energy stored in an arrangement of atoms. What this just means is, how are the molecules interacting? What is that force that keeps them together? Thermal energy is the energy of a substance, and the energy it possesses because of the temperature, and associated with kinetic energy. So you think about molecules bouncing around, gas molecules bouncing around. As it heats up, all those molecules are getting faster and faster. So that's the thermal energy, and that's related to heat. Now, if you're taking, or if you've, well, you should have finished up lab last week, or the week before last, I should say. So you've seen a little bit about this, the units of energy. And we talked a little bit about the units in chapter 7. But the energy of units, the units of energy is called joules and represented by a capital J, not a small j. And this joules is equal to a kilogram times a meter squared, so an area, over second squared. Now, you also will see it in forms of kilojoules. So remember, kilo is 10 to the third. So 1 kilojoule is equal to 10 to the third joules. And that's more typically used if there's a large number. So anything greater than 1,000 is usually represented in kilojoules. And you've all heard of calories. So calories is another form of energy. Units, I should say, is another unit that we use to describe energy. And what this is the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. And you've heard of calories, but the nutritional calorie that you see on the, your pop bottle or your snacks is actually 10 to the third. So it's a kilocalorie. So when it says, oh, this chip only has like 50 calories, what that means is it has 50 times 10 to the third calories in there. And so there's this nice conversion. And if you've taken the, if you've done the lab, you should recognize this number. We'll see it again when we talk about specific heat. But 1 calorie is equal to 4.184 joules. So what does this all mean, and where is it going to? Well, there we go. All that was definitions that you have to be familiar with. Okay, you have to figure out and learn how and when to use these terminologies. Okay, when we talk about something moving, when we talk about thermal, we're talking about kinetic energy. When we are going for chemical breaking, or bonds breaking and bonds forming, we're talking about potential energy. We can calculate energies in calories. We can calculate energies in joules. We can calculate in kilojoules. Okay, but all these energies that we're calculating, that we're learning about, that we will learn about, has to obey the laws of thermodynamics. And the first law of thermodynamics says energy cannot be created nor destroyed. So whatever energy is in the universe now is the total amount of energy. You're not going to form energy. You're not going to do it. It has to come from somewhere. Now, we can go from one form to the other, like we saw with a car, right? The potential energy got transferred to kinetic energy, right? You can lose energy from one thing and that gained it. It can be transferred or converted, but it cannot be created nor destroyed. That means the total energy of the universe is constant. And when we say that, we can write that as a equation where the total energy is equal to the potential energy plus the kinetic energy. Because we saw that if you have everything in potential energy, right, it's not going to be moving, so you have no kinetic energy. Once it starts moving, it's losing its potential and it's converted to kinetic energy. But the total energy, the overall total energy, did not change. And when we think about the energies in the form of heat and work, it gets a little bit more complicated. And we're not really going to focus on the work definition of energy, but we're really going to focus on the heat. And some common misconceptions we need to get out of the way. Heat and temperature are not the same thing. Okay? So I don't know if you covered that in pre-lab, but temperature and heat are not the same. Temperature, as we saw in the previous definition, is proportional to the average kinetic energy. Okay? How fast things are moving. The faster things are moving, the more kinetic energy it has, the higher the temperature. So it's going to have fast particles. Heat is the total amount of energy transferred between objects. It is caused by a temperature difference. Okay? You have to use temperature to measure heat, but heat and temperature are not the same thing. Okay? Heat is the amount of energy. Temperature is proportional to a type of energy. Okay? The other thing to note is that heat will always pass from warmer objects to colder objects. Naturally, it's going to happen spontaneously. You don't have to force that interaction. And this heat transfer will continue until both objects receive the same, or achieve the same temperature. So if you are very, very cold and you get a thermal pack, you open it up and it starts to heat up, that heat is being transferred to your cold body. Okay? You're not giving away its cold. You're not giving away your cold. The heat is transferred to you and will continue until the temperatures of the thermal pack and your skin is roughly the same temperature. And we say that now when you think about it, when you open up that hot plate, or not the hot plate, the hot pack, and you put it on your skin, does all that heat go into your skin? No. Some of it goes into the air, right? You're not getting an efficient transfer. And we talk about heat flows in different isolated systems and different systems and surroundings. So whatever we single out or denote as a system, okay, can be arbitrary. We say, this is what we're studying. This is our system. That means everything else is our surrounding. So if we have a test tube of some chemical reaction, okay, and it's open to the atmosphere, kind of like the heat pack, right? That energy is not going to be just transferred to your system, but also lost to the surroundings. You have a closed system, okay, where energy can cross but mass cannot. So in an open system, this can be spilled, your open test tube can be spilled, and you lose stuff, the energy goes away too. Here in a closed system, you won't spill anything, but the energy won't be transferred. And the isolated, you won't lose energy and you won't lose mass. It's nice and isolated. And you could think about like that in insulators. If you have a nice thermal thermos, you won't lose the energy and the heat of your coffee.